Hello dear students, welcome to the power system class. In previous class we have seen uh, power in the single phase circuits. We have explored about the power triangle, active power, reactive power and apparent power. We have also seen reactive power compensation, how the reactive power get compensated. We seen how does the balanced three phase system looks like, and based on that what is the balanced three phase power. So in today's lecture we are going to discuss about the star connection and delta connection, and if time permits then uh, transformation from delta to star. So let's begin with the star connection, or in the other words we call it Y connection. So here in this image you can see this is a star connection. I'm quite sure you all have seen this earlier as well. So what happens in star connection is the similar terminals, either from starting end or finishing end of all three, you say, windings are connected together. And when we do so, the one joint gets formed. That joint is called neutral joint, or that point is called a neutral point. Okay, and then we take one wire out from neutral. So here you can see this one. This one is R, this one is Y, and this one is B. So three different windings connected together, either you from the start or end, doesn't matter. And then a neutral point is called out. Neutral point is taken out of that. Now the remaining three terminals, these three terminals L1, L2, and L3 are also taken out. And this L1, L2, and L3 indicates three different line voltages L1, L2, and L3. So the voltage which will be measured between these terminals, not all three connected together, like between L1 and L2, as this one is R and this one is Y, so we call that voltage VRY. Okay, no, sorry, apologies. The voltage between yeah, this voltage between L1 and L2 is called VRY. And and voltage between this L2 and L3, which is the VY and VB. What is it called? It is called VBY or VYB. Similarly, the other one. Okay, so the voltage between these L1 and L3 are between these lines are called line voltages, and the voltage between any two lines. Okay, these any two lines, doesn't matter is it L1 or L2 or L2 or L3 or anything, any two lines is called line voltages. And voltage between two phases voltage between two phases are called phase voltages. Okay, so this here RY, VY, and VB, which is voltage between this VR and neutral point is phase voltage. Again, VY and neutral point is VY, phase voltage. And between VB and neutral point is again phase voltage. Okay, it is called VR, VY, and VB. And all these voltages are phase shifted from each other at 120 degrees. All these voltages are phase shifted 120 degrees apart from each other, as you can see in this phasor diagram. Here we have VR, we have VY, and VB. Okay, they are all phase shifted from each other. The magnitude of them are equal, similar. Okay, and if I want to find line voltage from this phasor, what did I do? We already have reference here. Vr we have over here. Then what we do with Vy, we stretch it in the negative side. So this vector which is shown by dashed line will be called minus Vy, right? Because we called it, we dashed stretched it out in the negative side, so it will be called minus Vy. And when we take vector sum of this Vr and minus Vy, we will get this resultant vector, and we will call this resultant vector Vry, as it is between two phases Vr and Vy. Okay, so we will call it Vry and it will be my line voltage. Okay, it will be my line voltage. So always remember, between in star connection, voltage between two lines is called line voltage. Voltage between two phases is called phase voltage. We can see here as well. See, between two lines and between two phases, right? Always make sure, uh, whenever you are going for star connection, if it is uh, voltage, then line voltage is always root 3 times of phase voltages. But the line current and phase current are similar. Line current and phase current are always equal. Why is that, you say? Because if you pay close attention, that it is very similar to what we have in series connection, right? Like if there is no if I tell you that there is no current flowing, or is if this part is open circuited, then this two will be called in series, right? So voltage will always be root 3 times into Vp, or V phase. Here VL indicates line voltage, Vp indicates phase voltage, and current will always stay same. So line current will be always equal to phase current. Now power due to one phase in star connection will be Vp into Ip into cos phi. Here Vp is again phase voltage, Ip is again phase current, and cos phi is power factor. Okay. But if you want to measure the power of three phase, then again it will be what it will be. It will be P is equal to 3 into Vp Ip into cos phi. Vp and Ip indicates phase voltage and phase current. But if when we convert that phase voltage into line voltage, remember we just discussed line voltage is equal to root 3 times of phase voltage. So if I want to convert this Vp into VL, then what do I have to do? I have to send this root 3 in the denominator of VL. So if we take that, uh, root 3 times root 3 will be 3, so 1 root 3 will be cancelled out, and the total power will be P equal to root 3 times VL IL into cos phi. So P will be equal to root 3 VL IL into cos phi. So that was a star connection. Now coming to the delta connection. So here in an image you can see this is a delta connection. What we have done here, like uh, we have again three terminals R, Y and B, and what we have done here, the ending terminal of R winding is connected with the starting terminal of Y winding. Ending point of Y is connected start with the starting point of B, and ending point of B connected with the starting point of R. See, so the finishing terminal of the first winding is connected to the starting of the second winding. So basically we are doing only that. Okay, and by doing that we have formed a close connection, or you can say close terminology, right? And this terminology is called delta connection or mesh connection as well. Okay, by joining them joining in this pattern. And then what we have done, we have taken three wires out. Here we have taken L1, L2 and L3 out. Okay, now if I tell you that there is no current flowing between one winding, then what it will be like, now if they are all three of them are connected in parallel with each other, hence, uh, please pay attention, I'm repeating one more time, all three of them connected with each other in parallel connection, as you can see, the line voltage here will be different from the phase voltage. Okay, sorry, line current will be different from the phase current. Apologies. So line current will be root 3 times of phase current, and voltage here will be remain same. Line voltage and phase voltage will be equal. So the voltage between L1 and L2 will be equal to L2 and L3, and also will be equal to L1 and L3. Okay, but the current here will be different. So line current will be root 3 times of phase current, and total power again here too will be as similar as it was in the star connection, root 3 VLIL into cos phi, or 3 VPIP into cos phi. Okay, and here VL and IL are indicating line voltage and line current, and VPIP was indicating phase voltage and phase current. So what are some applications of this star and delta connections? So one major application, if you have studied in previous power system courses, or if you have seen any of power system things, so you might remember that in transmission line, when generation takes place, after generation takes place, what do we do? We During the transmission, we convert that generated voltage from star connection to delta connection, and then the delta connection will be transmitted through the transmission lines, because delta will have only three wires. There is no neutral present in delta, as you can see here. Let me take you back. As you can see, there is no neutral here. So delta connection will be used at transmission, like first when power is generated, it is converted from there is a star delta connection. Star delta connection is provided there, and when after transmission, when power reaches to our distribution system, there is a delta star converter given there. It will convert my three phase delta from three phase star connection. Okay, other examples we can say, we have three phase alternators. It has three windings, and they are connected either in star formation or delta formation, right? Synchronous motors, induction motors, right? All they have either star or delta connections in them, in either in their stators, right? And in transformers, if you have seen, in three phase transformers, there also either star or delta connections are provided on both primary and secondary sides, right? Of winding, primary and secondary windings, right? Now let's come to transformation, delta star transformation. If I want to convert my this delta connection into star connection, what will I need to do? Okay, but before going to that, before jumping to what do I need to do, there are few conditions for converting my star transformation or star connection into delta connection. So first, let's see what are they. So first condition is um, equivalent network. It says if the two networks are equivalent, then only we can convert the star connection into delta connection, which means two networks as when two networks, when will you call uh, a network an equivalent network? So when two networks are said to be equivalent network if and only if the resistance measured between each pair of the terminal are identical. Okay, what does it means? It means if R12 resistance here, R12 resistance is, let's say, 5 ohm, and R12 resistance is connected between terminal 1 and terminal 2, then this resistance, which is on the star connection between terminal 1 and terminal 2, should also be equal to R12, which means the this and this should be equal to R12, which is 5 ohm first, let's say. So it should also be 5 ohm. Okay, so that is the primary connection, primary condition it must satisfy in order to convert my delta connection into a star connection. Okay, so let's how do we start it? Let's start it with uh, first considering resistance between node 1 and 2, right? So let's come here. See, this one is node 1 and this one is node 2, right? Node 1 and node 2, here you can see. So if I have to find the resistance between two nodes, node 1 and node 2, can't we say that this resistance R12 is in parallel connection with these two, R31 and R23, right? See, because this one is going there, right? And can't we say that as connection is taken here and there is no connection, anything connected at node 3, can't we say that R23 and R31 are in series with each other, right? So R23 and R31 are in series with each other. So it will be added up simply, and they are both in parallel with R12. So can't we write it like R12 parallel with R31 plus R23, because R31 and R23 are again in series connection. And if you remember the formula of parallel connection, 1 upon R equal to if RA and RB are in parallel connection with each other, then 1 upon RAB equal to 1 upon RA plus 1 upon RB. So applying similar here, we will have the resultant resistance will be R12 into R31 plus R23 divided by R12 plus R23 plus R31. Now again come here. This time we will consider node 2 and node 3. So when we are taking that, can't we say this two, R12 and R31 are in series with each other, right? See, and then R23 is in parallel connection with these two. See, R23 is in parallel connection with these two. So again, can't we write like this? R23 is in parallel with R12 and R31, because R12 and 31 are in series. And again R23 R dash 23 will be equal to, which means equivalent resistance of all three. Okay, it's nothing but equivalent resistance, so it will be equal to R23 into R12 plus R31 divided by R12 plus R23 plus R31, right? And in the last we take node 1 and node 3, and if we consider that, then R12 and R23 will be in series and R31 will be in parallel with both of them. So what we will be left with, we will be left with R dash 31 is equal to R31, which is in parallel with R12 and R23. These two are in series and this one is in parallel with both of them, and we will get R dash 31 equal to R31 R12 plus R23 divided by R12 plus R23 plus R31. Okay, very basic, we are very simple, right? Now this was from the delta side. Now let's go to the star side, what it will be. So remember in initial condition, what was the condition? That the resistance, equivalent resistance between this node and this node are node 1 and node 2 of delta side will should be equal to node 1 and node 2 of the star side, right? Which means this this 2 should be equal to R dash 1 2, right? So what will be the let's find out what will be the value of resistance between node R1 and node R2. As you can see, connection is only provided between R1 and R2, so R3 is open circuited. which means there will be no flow of current in this resistance R3, which means zero current. So we will be left with these two only, and when we will be left with these two only, can't we say both of them are simply in series? So it will be R1 plus R2. Okay, R1 R dash 1 2 will be simply R1 plus R2. Similarly here, when we are taking node 2 and node 3, we are taking node 2 and node 3, which means node 1 is open, it is not connected anywhere. As it is not connected anywhere, then there is no current flowing through the resistance R1, which means it is open circuited, which means, what does it mean? It means R2 and R3 are in series connection with each other. So R23 dash will be equal to R2 plus R3 simply, and again similarly R31 dash will be equal to R1 plus R3. Now as we said, it should be equal, which means what we will do, we will compare them with each other. Okay, so we will compare this R12 dash of star connection with R12 dash of delta connection. So by comparing them, here what we get, and we will compare them for all three of the formations. Okay, so by comparing them, what we will get, we will get this R12 R1 plus R2, apologies, R1 plus R2 will be equal to R12 into R23 plus R31 divided by R12 plus R31 plus R23. We simply, what we do, we simply compare this with this, again this with this, and this with this, right? Very basic. So we did for all three of them and we got this results: R2 plus R3 equal to R23 R31 plus R12 upon summation of all three resistance. Same, R3 plus R1 equal to R31 in bracket R12 plus R23 divided by summation of all three. Now let me show you an interesting thing. Now the final goal is to find value of R1. Okay, R1, R2 and R3. Okay, so how do we find it? So let's take the subtraction of these two values. Which two? This one, this equation, the first equation, and the next equation to it. Okay, so when we subtract R1 plus R2 minus R2 plus R3, so R2 will get cancelled, we will be left with R1 minus R3. So here you can see R1 minus R3, which will be equal to what it will be? It will be equal to multiplication. If we multiply R12 here inside, so we will get R12 R23 plus R12 R31, right? So here we have R12 R23 plus R12 R31, again R23 R31 R23 R12. So here we have R23 R31 R23 R12. Now again see R12 and R23 and R12 and R23, they are getting repeated. So what we will do, we will cancel them out. So when we cancel them out, cancel both them out, we will be left with R12 R31 minus R23 R31. So here we have R31 in common, so we will take it outside. So R31 in bracket R12 minus R23 divided by the denominator as it was. Okay, now I have to find the value of R1. So can't I find it if I add this equation, the equation which I just formed with this equation? See, so we will add these two equations. So what we will be left with? R1 minus R3 plus R3 plus R1. So minus R3 and plus R3 will be get cancelled. R1 plus R1 will be 2R1. Okay, and when you take the multiplication of both of these terms, R31 R12 minus R31 R23 and R31 R12 plus R31 R23, we will be left with R31 into 2R12. okay, divided by the denominator as it was. So this 2 and 2 will get cancelled, and we will be left with r1 equal to r12 into r31 divided by r12 plus r23 plus r31. Similarly, if you want to find the value of r2, what we will do, we will simply put the value of r1, this value of r1 into this one, this equation, right? And when we do this, we will get this value of r2 will be equal to r23 into r12 divided by r12 plus r23 plus r31. And similarly, the value of r3 will be equal to r31 into r23 divided by r12 plus r2 plus r31. See what is the key here. If you are looking for r1, then all the resistance which are connected with r1 will be mentioned in the numerator, and in the denominator there will be total sum of all three connections. Okay, same you can see here, r2 and connected resistance with r2, r23 and r12, and in denominator summation of all three, and same with r3, the resistance connected with r3, and denominator the what we call summation of all three. Okay, now this is the derivation. If you want to use it in if you want to use it in general, you will get sums for star delta and delta star transformations. So if you want to use it in sums, you can find it using that. See, you have this delta connection, you have r31, r12 and r23, r31, r12 and r23. Okay, so if you want to find resistance between r31 and r12, what you will do, you will multiply, which will be called r1 of course. So what we will do, we will multiply r12 into r31 divided by whole r. Here whole r is equal to sum of r31 plus r23 plus r12. Okay, same way if you want to find the resistance between r31 and r23, what we will do, we will multiply r23 with r31 and divide it by the whole r. Again the whole r is r12 plus r31 plus r23. Okay, and similarly with the r2, when we want to find the resistance, equivalent resistance between r12 and r23, we will take the multiplication of both of them, r23 into r12 divided by the whole r. Okay, so that was the delta to star transformation. In the next lecture we will be seeing star to delta transformation, and I hope you have understood it. If you haven't, watch the video again, because this summation is very base of electrical engineering, and if you want to uh, make career in electrical engineering, then this is very base and you must learn this, because you will find it on each and every step of your life. As an electrical engineer, you will find delta and star connections, delta star transformations, especially if you are going in, if you are trying to make your careers in power electronics or power systems. Okay, so learn that. I will be seeing you in the next lecture when we will be learning star to delta transformation. Till then, bye bye, see you, take care, thank you all.